Problem 2. A solid uniform cylindrical pulley of radius 0.15 meters is wrapped with a light string, which is then pulled at a constant tension of 10 newtons. So I'm looking at this pulley with a string pulled with 10 newtons of tension. So then it would rotate that way. That would rotate that way. And it's a pulley. We know it has an R value of 0.15 meters. Okay. We're to determine the total amount of work done on the pulley. It's not moving. We don't have a force times distance. But what is the work doing? The work is busy rotating it, right? And so we have, instead of a force times distance, we have, I should use the straight lined work. That way we don't get it mixed up with omega. Work equals, what's the rotational one? Not force times distance, but yes, torque, tau, times how much we rotate, theta. Okay. These problems will operate somewhat similar. We know what parts make up torque. What makes up torque? Force and radius. Okay. What makes up theta? I don't know what makes up theta, but I know that the distance that we could rotate and spin equals r theta. Is that true? Theta is a measure of rotation. So its units will typically be how much you have rotated, which is typically radians or degrees. Yeah. So I wouldn't say it's unitless per se, but its concept of unit is derived from it spinning. And so it hasn't moved. It doesn't have an actual physical distance. It has a difference in facing. Okay. So if work equals tau theta, what else can work equal? We can say that tau is force times radius. But then theta, what could we plug in for theta?
X over R.
Yes, x over r.
Cancel the R.
And again, our radius didn't matter, even though they told it to us. Oh, hey, look. This is the equation we started with. That work equals force times distance. But this is the distance that it travels around its circumference. Okay? So this would be kind of like relative to arc length. It's not necessary. Sometimes it's the distance the object travels. Okay? Sometimes it isn't. Force times distance. Wait, does that just mean we take the 10 newtons and multiply it times the 2 meters?
Yeah.
Okay, well then the answer's 20. Hey, look. We're good. We checked our answer.
Yeah.
We checked the answer they gave us. All right, let's check the next answer they gave us. Part B. Calculate and find the angular velocity. Okay, so that's omega. This is why I wanted to use a straight line W. For a 5 kilogram pulley. What's that?
M.
Okay. That was originally at rest. Omega initial equals 0. We're looking for the final angular velocity. We have M. We have an initial rotational speed. From the last problem, what do we know? We know work equals 20 joules, and that 20 joules is used to spin the object. So as we spin it, we could figure out how fast it's going because work is the change in kinetic energy, or 1/2 I omega final squared minus 1/2 I omega initial squared. This side of it is 0. Right? So we don't have to worry about the initial energy, because the initial energy is 0. Yes, we're talking about a disk pulley, so it's 1/2. The I value for this is going to be 1/2 mr squared. I equals 1/2 mr squared. And then omega,
Is what we're trying to find.
yeah, we don't need to rearrange it. Omega final squared. I was about to say, oh, look, hey, look, your radius is canceled out because it's v squared over r. But actually, we don't even need to go that far. We are looking for how it rotates, the angular velocity. We're not linear velocity. So
Equal W.
we have 20 equals 1/4. M is 5. R is, in the previous part, 0.15 squared. 1/2 mr squared omega squared. 4 times 20 divided by 5 times 0.15 squared, and then equals omega final squared, and we take the square root of both sides. Okay, mathematically, there's an issue with this mathematically that we didn't track. What else do you need to know in math class?
Plus or minus.
Plus or minus? In this case, what did plus or minus mean for our angular speed?
Counterclockwise or clockwise.
So it could be moving either direction. Does it work moving either direction? Are both of those a resemblance of energy? If you move counterclockwise, do you have energy? It's energy. If you move, wait, I said clockwise or counterclockwise? If you move the other way, is it energy?
Yeah.
Okay. So again, energy is directionless. It didn't matter if it's plus or minus, it's direction. Okay.